Okay, our third video in the series for Thermodynamics Paper 2, 1 through 10 are in the first two videos. Here's number 11. So this is interesting. Question bank duplicated number 11 as number 12. I don't know why I did that, and should have not just put it there, but now I can go and eliminate number 12. All right, 11. Monatomic ideal gas trapped in a cylinder by a piston. Following data are available. We have the initial pressure, we have the initial temperature, and we have the quantity of the gas. This says adiabatic expansion to a volume of 8 times 10 to the negative 5 meters cubed. And we're going to have three processes here. We're going to have an adiabatic expansion. We're going to have an isobaric compression. And then later, we're going to have an isovolumetric return to start. So there are three things in the cycle. That's why sometimes it helps to read the whole problem before you start solving it. So we have three different aspects here. And so here's our cycle. We go from A to B on an adiabatic curve with no heat. Then we go from B to C with an isobaric line, a decrease in volume. So there's zero change in pressure, and there's negative work there because I am decreasing in volume. And then we have from C to A, that's an isovolumetric line. There's no change in volume, so there's no work being done on or by the system. And so that's our cycle. So we can kind of make a table of things that we know and things we can calculate. So pressure, volume, and temperature. We also know that we're given that the number of moles is 6 times 10 to the negative 4. So here's what we know so far. We know the starting pressure and temperature, and the expansion goes up to 8 times 10 to the negative 5 meters cubed. Based on the numbers we have, we can figure out the volume at A. And so from PV equals nRT, we get 3.5503 times 10 to the negative 5 meters cubed. I'm going to round to 6 significant figures to avoid for rounding errors. I think 6 sig figs should do it. Okay, so then AI says what's the pressure of the gas after the adiabatic expansion. Now you know the starting pressure and starting volume. I know the volume at B. I need to know the pressure at B using the adiabatic relationship. And that 3.55 times 10 to the negative 5 meters cubed, which is right over there, is obviously needed for this, but I already solved for it, so yes, that's legit. And so if we work this through, again, I'm trying not to round here, so, and we wind up with 25816.9 pascals, which is less than the 100,000 that it had previously. And that matches the graph showing that from A to B the pressure decreases adiabatically. 25816.9. 25816.9 pascals. Okay. And that agrees with the mark scheme. Now it's asking for the work done. Well, we could say that the work is P delta V, but the pressure is not constant, so that's not going to fly. Instead, we're going to look at, and this is where, so we have, we can't use W equals P delta V because it's not constant pressure, so we have Q is delta U plus the work. There's no Q because it's an adiabatic process, and so therefore the work that we're looking for is negative the change in the internal energy. Now that change is 3/2 nR delta T. There's the negative in there. Don't sleep on that negative right there. I'm going to highlight it instead. Okay, so we have 3/2 nR delta T, and put in the 3/2. N is there as the number of moles. We have R, and then the delta T is the final minus initial, the temperature at B, minus the temperature at A. We know that the temperature at A is 712 K, but we can get the temperature at B. This is 414 Kelvin. Let's get a precise number. So we can actually kind of do that here. I mean, what work needs to be shown? Yeah, it's 3 marks. So they're going to want to see, here's the work right here for finding temperature. But I don't like their rounded numbers. I don't like when they use rounded numbers in intermediate calculations. Okay, so when we do PV equals nRT for B, we get a temperature at B of 414.230 K. And there is our work, negative 2.22702, which rounds to 2.23 joules. Then we have isobaric compression until its volume is equal to the initial volume. So from B to C, we have the volume going back to the original volume. Okie doke. I'm also going to start to keep a tally of the Q delta U and work for the processes. So while I'm here, we know A to B is an adiabatic process, so there's no heat there. We know that the system goes back to the original, it goes back to A, so the delta U for the whole system is 0. Here's the work for the first process, we just found that. And then B says we go back to the initial volume, we wrote that. Calculate the energy removed in the isobaric compression. Okay. So, now classic Mark scheme not really explaining itself very well. So where the heck are they getting this P delta V, 3 has P delta V, what's up with this? Okay, so for an isobaric compression, and if we go back to this table here looking at BC, so we have constant pressure. So the volume is changing, which means the work is not 0. It's not isothermal, so the delta U is not 0. So since delta U and work are not 0, the heat's not 0. So none of these things are 0. We have to consider all of them. So heat is delta U plus the work, so that's 3 halves nR delta T plus P delta V. Now we want to have common, we can't have temperature and volume together like this. We need to keep things consistent. So with a constant pressure, a change in volume is proportional to a change in temperature. P delta V equals nR delta T. Why do we care about this? Because I can take the 3 halves nR delta T and turn that into 3 halves P delta V. Boom. And that explains where this is coming from. So the P delta V, that right there, here, that's work. And then the 3 halves P delta V, that's delta U. And so we have P delta V plus 3 halves P delta V gives us 5 halves P delta V. And so the Q there is just going to be 5 halves times the pressure times the change in the volume. That keeps things simple. Now, I'm not going to use their rounded numbers. I'm going to use the non-rounded numbers, or at least the numbers we rounded to 6 significant figures from the data table. So instead of 25,800, we will use 25816.9. And instead of 3.55 times 10 to the negative 5, we'll use 3.55003. I don't think that's going to matter. But we'll still use it. Like I said, I don't know that it makes much difference. 2.87211 joules is what I get. And then in the last part, BII, it says the gas is returned to original state in an isovolumetric change, which means that the volume doesn't change, so there's no work done. Energy supplied is 3.9 joules. Okay, isovolumetric, so there's no work being done there. And it said there's 3.9 joules of heat being inputted, is that a word? Into the system. And it wants the efficiency. So let's see what we can continue to fill out in this table. So I kind of like to change the color when I'm filling out tables based on things that I know. Can I put in, do I know the pressure of C or the temperature at C? Do I need to know those things? No. I could figure them out. Could I? Actually, I know that I can because this is the second time I'm doing this problem, so I know I can calculate those things, but I don't really need to right now. I'm more interested in the energy balance table here. So I solved for the work for AB, which was positive. I solved for the heat in BC, which was negative. It told me that there's 3.9 joules going in for CA, and there's no work done because it's isovolumetric. Like I said, the cycle goes back to start, so there's no change in the delta U. Let's see what we have. So we have 1.02789 joules. Since there's no change in the internal energy, and Q is equal to delta U plus the work. Let's not forget that. So if there's no delta U, then that's all work. Positive 1.02789 joules of work that is done. So if there was no work done in CA, that means the work for BC is the difference between the work that was done in AB and the net positive work. So negative 1.9913 joules was the work for BC. And the delta U is going to be the difference on all of these guys. So for here, we have 2.22702 joules. And in BC, there was a little bit of everything. So the Q was negative 2.87, blah, blah. The work was negative 1.99, blah, blah. And so the delta U, there's my delta U for BC. And then finally, for CA, when there was no work done, that delta U has to be entirely 3.9 joules. Oh, the difference in negative sign means it's a negative sign on the AB delta U, because if Q is 0 and the work is positive, the delta U has to be negative. And yes, now all of these values match up. We have our complete accounting of energy that's done. And so for efficiency, it asks for the efficiency. I'll just kind of write it here. We have the efficiency is two ways of doing it. Be careful on the heat. The total work put in is not the net. I guess when I write total, I should be saying net because we got positives and negatives. So the total Q in is the 3.9. It's not asking for the net heat. So, but the useful work is you got to consider both the work that's done by the system and on the system, positives and negatives. So that's why I'm using the net work. And so I wind up with 26% for my net work. I'm sorry, for my efficiency. Efficiency. I've been doing this. I need a break. So where is the efficiency question? Energy removed. We did that. Efficiency. There it is. 26%. Which is correct. That's what we got. Now, I wanted to point something out here about the efficiency that they calculated, and this tripped me up before. They are not using the formula in the data booklet, right? 3.9 minus 2.87 over 3.9. Like, what is that, right? That is not, the 3.9 minus 2.87 is not, let's go back to our table. That has nothing to do with the useful work. In fact, the 3.9 minus 2.87 is the net heat. So you can still do it that way. You can still kind of say like, oh yeah, another way of looking at efficiency is not necessarily the useful work over the input energy, which is the formula from the data booklet. You can also look at it as like output over input. Like, what are you getting out versus what are you putting in? And so this is kind of like, this is the net output heat, like, which winds up being positive. So the system still put heat out of that of the cycle, and then the 3.9 is the input Q. So you can also look at efficiency that way. You still get 26%. All right, so there's that. And then BII says, why is it important that engines are designed with high efficiency, even though all engines obey first law of thermodynamics? This is a gimme. Like, you want to minimize energy waste. You want the useful work to be as close as possible to the energy input, beneficial to the environment, et cetera, et cetera. So there you go. All right, that is number 11. And then number 12 was a duplicate of 11. So now we're on number 13. We have another pressure versus volume graph. They love these things. There's 3 parts in this cycle. We have an adiabatic cycle right here from A to B. So we have 0Q on AB. Isothermal, which is from C to A, actually. Oh, wait a minute. Sorry. The adiabatic, why is it just naming it in order? The adiabatic always has the steeper curve, so that is the CA cycle is adiabatic, so there's no Q there. The isothermal is the shallower curve, and that is AB. And then we have the isovolumetric, obviously, from B to C, no change in volume. And then they tell us a bunch of things. Start values are pressure, volume, and temperature, and then they give us the pressures of B and C. And then it says YAC is the adiabatic part, and we'll go from there. I just went and checked. There's 3 more problem sets left, 13, 15, and 17. I think we should be able to fit it in this video. All right, let's go. Okay, I feel like 11 was a bit of a beast. Hopefully 13 is kind to us. So let's see. Why is AC the adiabatic part of the cycle? All right, interesting question. Why is AC the adiabatic part? Well, it's not going to be BC because BC is the isovolumetric for obvious reasons. But I have 2 curves, AB and AC, or CA. I happen to know that adiabatic curves are steeper anyway. I don't know if you could use that as an answer, but there's 2 possibilities. So if AB were adiabatic and there were no heat in AB, then Q would be 0 and delta U would be equal to the work. They would be negatives of each other. So it's an increase in volume from A to B. So that's positive work being done. So therefore the delta U would have to be negative. And delta U is N as 3/2 NR delta T. So that would mean a decrease in temperature. Okay, that's fine. But then in BC, there's a further decrease in temperature because there's a decrease in pressure at constant volume. So now I go cold and cold again. Then if AB is the adiabat, then CA would be the isotherm. And then you have a cold temperature returning to original state values at A. That's not happening. Or I have cold temperature. I need to get back up to what A was. So that's not going to work. But if CA is the adiabatic, then same logic. We have no heat in CA, so the delta U plus W equals 0. There's a decrease in volume from C to A, so that's negative work being done on the gas, negative work from the perspective of the gas. And therefore, it's positive change in internal energy, which means the temperature is increasing. And there's a temperature decrease in BC because, again, there's that decrease in pressure at a constant volume. So if AB were the isotherm, constant temperature, BC has the temperature drop, and then CA has the temperature gain, then we can bring the temperature back to its original state, and we are good to go. So that's why CA has to be the adiabatic curve and not AB. And those mark scheme alternates, they all kind of say the same thing. All right, so that the volume at C is 333 times 10 to the negative 2 meters squared. We're looking at C here, and we know values for A, so we're talking about the CA cycle here. Sorry, I said cycle, I meant process. And so since that CA process, we know that it's adiabatic, we are going to use the 5/3 relationship for A and C. We know the pressure and the volume for A. We know the pressure for C, that's given in this list right here. And so we are going to solve for the volume of C and show that it is about 3.33 times 10 to the negative 2 meters cubed. So that's pretty basic right there. Again, when you're we have the 5/3 relationship, but then when you're going to take the root is 3/5, not 5/3, right? So watch for that. Okay. You have a number of of different alternates there. This is the one that I would use, the adiabatic process. I mean, they just made a point about the fact that Ca is adiabatic. So that's B. Okay, we keep going. C. Suggest for the change A to B whether the entropy of the gas is increasing, decreasing, or constant. Remind me what AB is. It is the isotherm. Let's write that down. Okay, so looking at Q is delta U plus work, and we haven't seen anything involving entropy in a minute. So let's remember that the change in the entropy is the change in the heat per unit temperature. So we have a constant, it's an isotherm, so there's no delta T. So with no delta T, we're going to have no delta U. And we know we have an increasing volume, so that means that I'm going to have positive work, so that means I'm going to have positive heat. And so that would be positive heat is a heat increase, and at a constant temperature, being the isotherm, we're going to have an increase in the entropy. All right, D. Calculate the thermal energy taken out of the gas from B to C. B to C is the isovolumetric. All right, so there is no change in, no change in volume. I don't know if I just said this. No change in volume, so there's no work done, so there's no W, so the heat is going to be the change in the internal energy. And I don't know any of the temperatures, do I? I know temperature at A, whoop-de-doo, 602 Kelvin. But what I can do, and I did this in 11, and so instead of doing delta U is 3/2 nR delta T and figuring out the temperatures, we can say that delta U is 3/2 V delta P, which is, that's where this is coming from here. And then the volume of C, didn't we just find that? Yep, showed it the volume of C is 3.33 times 10 to the negative 2 meters cubed. So this right here, that is the volume of C. And so we're going to use that over here. So you have 3/2 times the volume of C times the difference in the pressures that was given. Those pressures are given in the problem for B and C. Pressure of B, pressure of C. We're going from B to C. 3. Now, interesting, instead of doing final minus initial, they actually, here they did the pressure at B minus the pressure at C, which I'm not really sure why they did that. They wound up with a positive answer. Should not have been a positive answer, because it even says in the problem, calculate the thermal energy taken out of the heat from B to C. There's a decrease in pressure, so that means there's a negative delta U, which means that the heat is negative. And it even says to calculate the heat taken out of the gas, not put into the gas. So, like, it doesn't even say the quantity. It says accept negative values. Yeah, no duh. Like, like, it is a negative value, so I don't really know why they did that. I mean, it's still, like, the quantity still comes out right, but that's weird. Okay. So that was D. And then we have E. Highest and lowest temperatures of the gas are 602 and 92 Kelvin. Efficiency of the engines about 0.6. How are these data consistent with the second law of thermodynamics? They're using the Carnot efficiency equation here for temperatures, which is N Carnot is 1 minus Tc over Th. So that winds up being, that's the maximum efficiency that it could be. And they said like 0.847, so that's greater than the 0.6 that they're experiencing. And so you can't be greater than the maximum efficiency of the Carnot engine. So the fact that that is greater than 0.6 is good to go. And so it says this engine has E less than EC as it should. Okay, let's power through. We have 2 more problem sets left. Let's go with 15. We have a piston with a gas. It says initial 3 thermodynamic processes in the cycle. Initial conditions, we have the volume, the pressure, and the temperature at the start of the cycle. Okay. And then they show part of the cycle here going from A to B. AB is an isotherm, and it says calculate the pressure, and it says in which the gas expands to 3 times its initial volume. Therefore, the volume at B is 0.990 meters cubed. And then it says, let me guess, it wants the pressure. Yep, pressure at B. So it's a use of PV equals a constant. That's because it's isothermal. And when we work that out, we get 43 kilopascals for the pressure at B. Maybe we'll throw that over here. Pressure B is 43 kilopascals. Don't forget that kilo is 10 to the 3, right? Okay, then we have gas undergoes adiabatic compression BC until it returns to the initial volume. So there's the curve going from B to some point C, which is at the initial volume, the same volume that A was at. And then it says, to complete the cycle, the gas returns to A via the isovolumetric process, CA. So there we have it. Sketch on the PV diagram the remaining 2 processes, BC and CE, that the gas undergoes. I just did that. There it is. The curves. Concave curved line from B to C with a higher pressure than A, and then vertical line joining C to A. Dunzo. Alright, that was B. Then what is C? There's the answer. Oh, they used a different color. That's interesting. Then C, showed that the temperature of the gas at C is about 350 Celsius. And then for C, so that is an adiabatic process from B to C. Do we have the temperature at B? We don't, but we have the volume and the pressure, so we're going to have to calculate the temperature. They have 2 ways of doing this. They have this TV to the 2/3 as a constant. That's new. I've never seen that. But I'm looking just at the adiabat. If we could go from B to C using the information of B's. We have one thing that I forgot to note was that the volume at C is the volume at A, which is 0.330 cubic meters. So I now have information for both pressure and volume for B. I know the volume of C. I can get the pressure at C. And then with the pressure and the volume at C, I can get the temperature at C. So let's use the adiabatic expression to get the pressure at C. Here we are, this guy here. So using the numbers, so I got the pressure at C, it's 268,331 pascals, or, let's see, pressure 268.331 kilopascals. Knowing those 2 guys there, I can get the temperature at C in Kelvin. Let's just do that here. Temperature at C. Oh, poo. They didn't tell me the number of moles, did they? How am I supposed to do PV equals nRT without that? Actually, scratch that. I'll use, now that I know the pressure of C, I could use the process from C to A. So yeah, because I don't know N, so I can't do that. But, so yeah, using that process, we can get 56 degrees. Let's see if that matches up with the answer. Where are you? Oh my goodness, no, it's much more. Let me go back, let me look at that again. Oh, I am the dunce. I fell for that, like, classic trap. We don't work in Celsius, all right? We got to work in Kelvin and then convert it back. Let's try 351 degrees Celsius, right? So yeah, always work in Kelvin. I made that mistake. I can't believe I made that mistake. So 351. Yes. There we are. 351. Yeah, I don't know what that TV to the 2/3 is a constant. I've never seen that. But I use the adiabatic process, the 5/3. I use two processes, actually. I use the adiabatic to get the pressure of C, and then once I figured that out, then I can use that pressure of C with the isovolumetric process to do pressure over temperature equals pressure over temperature, but work in Kelvin. That is a big deal. All right, so that is that. D, why is the change of entropy for the gas during the process BC equal to 0? This guy is easy. Let's remember that the change in entropy is the change in heat per unit temperature. And if there's no change in heat, then there's no change in entropy. E and F, are they kidding? Oh, gee. All right. E, why is the work done by the gas during the isothermal expansion AB less than the work done on the gas during the adiabatic compression BC? So work is P delta V, so the work is the area under the PV graph. And so if we look at the different curves, it says the work for AB is less than BC because AB is closer to the graph than BC is. So AB has less area under the curve than BC does. You can look at that answer key guy or look at the one I did. But yeah, area under the curve AB is less than the area under the curve for BC. So therefore the work done during AB is less than that for BC. It's all about that area under the curve. Okay, number F, quantity of gas. Oh, now they tell me that the amount of moles. Sheesh. Calculate the thermal energy removed from the gas during the process CA. So there's no, and this is no work done. The reason why there's no work, there's no change in volume, so there's no work done. So the heat removed is just the change in the internal energy. And what they're doing here is 3/2 nR delta T. They're using Celsius. I think that's tricky. I still recommend working in Kelvin. So it still winds up being the same number, 2.15 times 10 to the 5 joules. That's when you round it, it's 241,857 joules, but that's what you wind up getting. For F, okay, I'm over 30 minutes, but we just have one more question. Let's just squeeze this sucker in. It doesn't even look that long. It's just A and B. And so we have a pressure volume graph here. And so we have going from A to B to C. It says undergoes a compression and then an increase in pressure. Adiabatic process increases the volume of the gas to 5 times 10 to the negative 2 meters cubed, which we can see from the graph. I'll draw in that adiabatic curve. All right, there it is. Calculate the work done during the compression, the work done on the gas. And so we wind up getting 3,000 joules. The work is done on the gas since the volume is decreasing. So yeah, negative 3,000 joules. Then it says calculate the work done during the increase in pressure. That is mad easy. That increase in pressure is on an isovolumetric line. The volume isn't changing. If the volume does not change, there is no work done. And so that's 0 joules for that. Calculate the pressure following that process. This is kind of weird because they use values off the graph in some places, but not others. So basically they're going from C to A, since they're using PV to the 5/3. I'm also not sure what they mean following this process. Following what process? The increase in pressure? So anyway, yeah, and they're actually looking for the 87 kilopascals. That's That's at A. Because they're following the adiabatic relationship. That's the adiabatic relationship. But honestly, instead of A and B, it's really C and A. And you're looking for the pressure at A. So we know the pressure at C, that's the 4 times 10 to the 5. So this right here is the pressure at C. This right here is the volume at C. And you can see that pressure is 4 times 10 to the 5. Volume is 2 times 10 to the negative 2 for point C. And then you have the pressure at A times the volume at A, which is 5 times 10 to the negative 2. And so when you work all those numbers out, you wind up with a pressure at A. Let me fix this. Pressure, come on. My pen does not want to work. Pressure at A is 8.7 times 10 to the 4 pascals, and if we're using kilopascals, that's 87 kilopascals. All right. And then it says, outline how an appropriate adiabatic change can be achieved. Like, in other words, how are you going to do it? So it means no transfer of heat. So if you're going to have no transfer of heat, you better be fast, and then you also need to insulate in order to get that to work. Okay. That is the end of all of the questions. This is the third video of 3 for B4 Thermodynamics Paper 2. Thank you.